Welcome to your introduction to renal physiology here with SPFD. These videos are intended to be short introductions to the material that you will see in class. They will be most helpful to you if you listen to them before you hear the lecture. This may take place of any pre-reading that you do on a topic, or if you're like most students who don't have time to pre-read, then you can listen to this while you're eating breakfast. Okay, let's get started. So you've just finished the cardiovascular and pulmonary systems. But the last bit of the information in the pulmonary section that you were not tested on dealt with gas transport and pH control. We're going to transition into the renal system, picking up where the respiratory module left off. You've talked about pH in plenty of your courses before now. You've covered them in general chemistry during undergrad, and you've also seen them here at SPFD. The same rules that applied to them also apply now, but rather than a test tube, we're going to be dealing with the human body. As a reminder, the pH scale is the negative log of the concentration of hydrogen ions. So, when hydrogen ions are increased, then the pH will decrease, and vice versa. This low pH is associated with acidity. However, in the body, we will refer to this as acidosis. But we have to remember that the pH scale is logarithmic, so very small changes in hydrogen ion concentration can have drastic effects on the pH. The human body is not set around a neutral pH. We operate at what technically is a basic pH. The normal range for human blood pH is between 7.35 and 7.45. So these numbers are some that you have to commit to memory. So if we were going to take a blood gas and find out that the pH was 7.2, we would refer to that as an acidosis. Conversely, if we did a blood gas and we found out that the pH was 7.6, we would conclude that they were in a state of alkalosis. However, this blood gas doesn't tell us all that we need to know, which takes us into today's lecture material. A pH alone just tells us whether we're in a state of acidosis or alkalosis. This is just a snapshot in time. We need more information to know whether the change is acute or chronic, or whether we're getting better because of the body's built-in compensation mechanisms, or we're headed down the wrong road. The body's pH is regulated via a buffer system. The plasma proteins act to buffer immediate changes in pH. The lungs work to regulate the body's pH on a minute-to-minute basis, and the kidneys kick in on a chronic or day-to-day basis. This reaction is another one that we will need to learn, memorize, and understand how to manipulate. The kidneys deal with the ionic aspects, while the lungs deal with the CO2 aspects of the equation. Let's take a look back at the lungs and the respiratory system. Here we see gas exchange across a capillary membrane. We're offloading carbon dioxide and taking in oxygen. Our lungs are essentially a mechanism to get rid of the waste products of cellular metabolism. So, if we increase the respiratory rate, then we would be increasing the rate at which this exchange occurs. This is referred to as blowing off the CO2. We can measure this clinically. We measure the CO2 in the arterial or venous system, and we can also measure the amount of CO2 that we expire. Last week we went over the PaCO2, or the partial pressure of CO2. As a review, we looked at PaCO2 and saw whether it was over or under 40 millimeters of mercury. We associated a PaCO2 of lower than 40 with hyperventilation. Additionally, we said that a PaCO2 over 40 was associated with hypoventilation. However, we made a clear delineation that there was no actual respiratory rate that correlated with hyper or hypoventilation. But we should know that a normal person with excessive tachypnea or a high respiratory rate will be hyperventilating, therefore blowing off their CO2 and sending their PaCO2 down. We have a normal parameter for CO2 in most people. It should be between 35 and 45 millimeters of mercury. When we blow the CO2 off and send our CO2 down, it is termed a respiratory alkalosis, and this correlates with a PaCO2 of less than 35 millimeters of mercury. Conversely, if we're not blowing the CO2 off, it would build up in our body, and this will send our PaCO2 higher. And if it went above 45, this would be termed a respiratory acidosis. Take a look at the ending of the pH and respiratory CO2 numbers. Both end in 35 and 45. Many physiologists will take the middle of the road and think of normal as 7.4 and 40. But as clinicians, you must know the ranges for normal. As we will come to learn, the kidneys are a complicated filter. One of its mechanisms is to regulate our plasma ion concentrations. The ones important for today are the hydrogen ion and the bicarbonate ion. If the body needs to increase its plasma pH or become more basic, then all it would need to do is either absorb more bicarbonate ion or lose hydrogen ions in the urine. Conversely, if the body needed to become more acidic or drop the pH of the plasma, the kidneys could either absorb more hydrogen ions or just not reabsorb the bicarbonate ions. When we look at this from a clinical standpoint, we look at the pH from the blood gas as before, but now we're going to add in serum bicarbonate. The physiologist will tell you that the normal bicarbonate level is 25, but as clinicians you may be able to accept a normal range, and this may be between 22 and 28. Many texts have different levels of normal. Be sure to look at the reference range given by the lab. So, if we draw blood and found an elevated bicarbonate, we would think of this as an alkalosis. On the flip side, low serum bicarbonate numbers are associated with acidosis. The final part of this introduction is the concept of a primary disturbance versus compensation mechanism. The body wants to maintain a normal pH, but certain disease states can alter this normal balance. If the underlying problem is metabolic, then there needs to be a respiratory or CO2 compensation. If not, then the pH of our blood may change. The final part of this introduction is the concept of a primary disturbance versus a compensation mechanism. The body wants to maintain a normal pH, but certain disease states can alter this normal balance. If the underlying problem is metabolic, then there needs to be a respiratory or CO2 compensation. If not, then the pH of our blood may change. If the problem stems from a primary respiratory mechanism, then the body's compensation in a few days would be to regulate the plasma concentrations of the bicarbonate ion. The tricky part to the acid-base disturbance is that this only scratches the surface of the complexity that is pH disturbances. More factors are in play, but this is a start. The best way to get comfortable with these concepts is to do practice problems and then think about the disease states that you've already learned and what may happen to their acid-base status in these types of patients. So, we're going to do a few of these practice problems. I'll give you the answers after class, but I want you to be thinking about this before class, and then when you get the information from class, try and answer it for yourself. So, what would happen to a patient who overdosed on opioids who slowed their respiratory rate? What does their pH look like? What does their PaCO2 look like? And what about the bicarbonate? For patient number 2, let's say this patient has an underlying metabolic acidosis. This is his primary problem. The next thing that we know is that he has a respiratory rate of 40. This is likely a respiratory alkalosis to compensate for the underlying acidosis. But let's say that you place this patient on a ventilator and set their respiratory rate at 12 breaths per minute. What would happen to this patient's pH? What about their PaCO2? What about their bicarbonate? Think about these things during class, and afterwards I'll give you the answer, and if you have any questions, please come see me. I hope this was helpful. If you have any suggestions or you want me to change something, please email me or come see me.